Hello, ISyDMA’5 colleagues. I would like first to thank Professor Muhammad Ashur, who did really start this great conference, and his organizing committee for all the trouble they took to have this conference continuing. We were delighted and honored to welcome you in Jordan during ISyDMA’4, and we hope you all have good memories of Jordan. And we are delighted to be part of this conference. So today I will present a talk in addition to several papers by my students and colleagues. Today I will present a paper titled Using Polystyrene Nanolayers as a Coating Material for Field Electron Emission from Metallic and Semiconductor Cathodes. I would like to give an introduction as to the importance of this and the reason behind this work. From studies of the microscopically localized electron emission process that is responsible for pre-breakdown currents flowing between vacuum-insulated high-voltage cathodes, it became evident that electrons can be cold emitted from dielectric microinclusions at the surface at fields that are lower by two orders of magnitude lower than the threshold value needed for cold field electron emission from metals, which is equal to about 3 by 10 to the 9 volt per meter. In order to simulate this system, techniques were developed to fabricate and test composite microemitters consist of metal or semiconductor substrate of non-microscopic profile covered by submicron thick layer of suitable insulating material. Parallel objective of such type of study was to determine whether such composite emitters had any technological potential as cold electron source that could be used in such commercial devices such as the electron microscopes. Of course, their performance can be characterized in terms of beam brightness, emitter lifetime, short and long-term current stability, and previously we incorporated the energy spread measurements also. Several materials were used to coat the core material, the tungsten and the carbon fibers used, such as several types of epoxy resin, hydrocarbons, alumina, lacquer, plastics, zinc oxide, magnesium oxide, zirconium carbide, and tetracyanoethylene, carbon black, etc. Several materials were used. Today, we are presenting work by using the polystyrene nanolayers to coat both tungsten metal and carbon fiber, we can call it semiconductor cathodes. This study is about the effect of the coating of both types, tungsten and carbon fiber tips with polystyrene layer, and apply the field emission techniques for measurements. The base sample tips were prepared using the normal procedure of electrochemical etching. The coating material consisted of a solution of polystyrene and toluene to create the composite sample. Then the clean tips were installed at the FEM locally installed field emission microscopes under high vacuum conditions and were tested in clean mode before coating, and then after coating, and comparison were made between the two modes. Techniques were employed to use Fowler Nordheim FN and Murphy-Good MG plots to characterize the results. let us say that there are no known theory to cover for the coating layers and mechanism of emission. So SEM, scanning electron microscope, were used to study the profile, and the field electron microscope images were used to study the changes that occur in order to compare the two mechanisms before and after coating. We can say as an introductory result that this coating, like most of the other coatings, produced or showed significant improvement in the electron emission current values that needed lower applied voltages for both types of composite materials. Field electron emission. Let me introduce a simple definition. The field electron emission is the emission of electrons from the Fermi level of a metal or semiconductor into vacuum, which is a unique quantum mechanical process of the electrons tunneling into vacuum. The materials that are normally used in our procedures were either base materials consisting of metal or semiconductor. The metal, as an example, is tungsten, and close semiconductor material is the carbon fibers. The coating materials employed in the study were polystyrene and polyethylene, will be introduced in a poster presentation in this conference. The field emission microscope, this is the tip here, and this is the screen that is coated with a layer of tin oxide to be conductive so the current can be measured, and here is the voltage put to the tip to produce the electron emission. The screen is coated also with a layer of phosphor in order to be able to observe the emission. And this is the computer by which we can record the measurements. And this is the traditional scanning electron microscope. Occasionally, we use the transmission electron microscope in order to measure the thickness of the layer when the materials for coating used were consisting of materials that the electron beam could penetrate through transparent layers. So it showed different layers. But in our case here, no difference in the layers were observed, so the SEM was used. Here is the data representation. This is the current voltage characteristics for a clean tungsten. This is about 800 volts. This is the standard, and the standard coated current voltage characteristics is presented here, where there is no electrons emitted until certain value of applied voltage by which the electrons are emitted to a value which we call it saturated current. It can increase, decrease a little without exploding the sharp tip until it comes to a value which is called V saturated. So this is the V saturated region, and then the current voltage have this path like this, and then the increase and decrease most of the time shows a hysteresis effect. Now the Fowler Nordheim plots, the Murphy-Good plots, and the Millikan-Lorentz plots. Millikan-Lorentz plots, those three methods were used to characterize the IV characteristics. This Millikan-Lorentz plots is an old technique, but still possible to produce some information, while the most used methodology is the Fowler-Nordheim plot, by which we plot 1 over V versus ln I over V square. Murphy-Good plots we recently introduced to characterize these steps, by which ln I over V to the power K, which is a certain constant value for the material, versus 1 over V, and those we are doing this great analysis using this new plots in cooperation with top scientists in the field, Dr. Richard Force from Surrey University. Now, the basic sample preparation. This is the sodium hydroxide solution. The composition, the concentration differs if it is metal or carbon fiber. So this is the cathode, which is a carbon rod, and this is the anode, which is the tip immersed to here until we have a power supply, and sometimes we have a switching device by which, when it is etched, when we turn on the power supply at certain current, it cuts at this point and produce this sharp tip. This is the tungsten sample, and this is the carbon fiber sample. Of course, it is known that it is much more difficult to work with carbon fiber samples. So it's a huge effort from our team to work on these carbon fibers. Coating materials preparation. The solution was prepared in different concentrations. For the purpose of the study, the solution was prepared using 4 grams of polystyrene dissolved in 50 ml of toluene and left under stirring for 3 continuous hours to produce a homogeneous solution. Composite emitter preparation. The coating procedure involved very slowly. It's important this very slowly, because if you don't dip very slowly, a ball will form, a drop will form at the edge of the tip. So very slowly dipping the tungsten or carbon fiber tip into the polystyrene, and then accurately and vertically removing it to ensure that only a thin film remained on the tip surface to obtain regular film. Composite emitter SIM images. This is the composite emitter of the tungsten tip. You can see the coating, and the composite carbon fiber you cannot see through because the carbon fiber is not real metallic, so you cannot see through. But this was the carbon fiber tip, and the coating was there. Clean tungsten field electron microscope pattern images. This is the image from clean tungsten. You can see some sort of 4 spots. If the tip was very clean, then you see the 4 spots more clearly. 1, 2, 3, and the 4th more clearly. But this is not a very clean tip, by means that the student who did the work did not clean the tip ultrasonically well after etching process. So this is the current voltage characteristics. This is the IV characteristics, the standard of the tip. You can see this is different from what we have shown before because of the not very clean tip. Now, this is the Fowler Nordheim plot, and this is the Murphy-Good plot, as we mentioned in details before, just to compare the two methods. And then, of course, this is for clean, and then we will talk about coated. Now, for the composite tungsten polystyrene field electron microscope pattern images, this is the same image, just enlarged here, just to show that there is a structure inside here. While in the normal epoxy resin, we did not see any such structure. It was just a bright spot without any structure. Now, this is the tungsten polystyrene current voltage characteristics. This is the increase cycle. Of course, this is the increase and the decrease cycle after the switch on phenomena occurred. So, with the metal, which is tungsten, we can see the coating produced a switch on phenomena, which we will not see with the carbon fibers. This is a normal procedure with carbon fibers, so it was the same with other coating materials. So this is the V switch. It happened at 2500 volts and produced about 11 microamperes. So this is the increase. There is no saturation region, very little, not really worth to mention. So this is the decrease, and then this is the increase. So it is almost the same with a very small hysteresis effect. The composite tungsten polystyrene data analysis. Here is the Fowler Nordheim plot. This is the Murphy-Good plot. This is the decrease when the emission current went down, and then when it is increased. So this will prove to be very important to analyze. Now it is not well-known characteristics or analyzed, but we are working very hard with international team to analyze this very important characteristics. Now we come to the pattern images, clean carbon fiber film pattern images. This is for the increase, for the increasing cycle. So it starts at 690 volts, 410 nanoamperes, and we end up with 900 volts, 1150 nanoamperes. Then this is the decrease cycle, and when it is reduced here, it is 550 volts for 372 nanoampere. It's very close and repeatable results. So in a bit, we can compare other coating effects. So we go down to the clean carbon fiber. So now we finished with the metal, now with the clean carbon fiber. This is the IV characteristics of the standard carbon fiber field emission tip, and this is the Fowler Nordheim plot, and this is the Murphy-Good plot, the increase and the increase for both cycles, and this is the decrease for the clean carbon fiber. This is the decrease, and then this is the clean carbon fiber analysis for the decrease. This is the Fowler Nordheim plot, and this is the Murphy-Good plot. Composite carbon fiber polystyrene coated field electron microscope pattern. You can see this is 470 volts, 240 nanoampere. And here we end up with 820 volts, 1480 nanoamperes. Quite an improvement. And this is for the decrease. You can see this is the same image, and this is the going down 510 volts for 594 nanoamperes. This is the composite carbon fiber polystyrene IV characteristics, the increase, and this is the decrease, the composite tip, the decrease value. So this is here 950 volts for 1800 nanoamperes, 900 for 1800 nanoamperes. So not much difference in this case. And this is the composite carbon fiber, and this is the Murphy-Good plot here in the increased cycle. And the conclusions: for tungsten samples, coating tungsten emitters with polystyrene was a successful process. We successfully produced the composite emitters. It improved the current values with reduced applied voltage value that is required for the same value of emission current. For the carbon fiber samples, the IV characteristics, the Fowler Nordheim plot, the MG plots for the clean and composite carbon fiber tips, along with the film pattern images, showed a slight improved performance as an electron source. This was repeated with another set of carbon fibers, different tip radius, and the results were the same. I would like to thank you all for listening to me, and I thank you very much for this opportunity. Good evening.